This video has a Halloween theme. There is a werewolf and a zombie. A video of a Halloween prank. Examples pertaining to ghouls, werewolves, and spooky things. There might be some bad singing, and by might be, I mean there is. Every Halloween, the zombies and werewolves gather in an underground tomb. They don't like Halloween because it's the one night where they can't scare humans. On Halloween, everyone thinks they are a small child in fancy dress. So they gather underground and bemoan how scary small children are these days. Invariably, they quarrel about who is scariest. The zombies argue that they are the scariest because they look rotten, but the werewolves believe that they are the scariest because they have big teeth. The zombies think the werewolves look too cuddly. Each year, Azal, head of the werewolves, becomes so enraged that he eats all of the zombies to win the argument. They taste rotten too. This year, the zombies are fighting back.
Who are you?
I am Cubit Zenom, king of the zombies.
Why did you come?
I come because I'm tired of you eating all of my zombie friends. I intend to prove once and for all that zombies are scarier than werewolves.
You lie.
I never lie, apart from in the ground sometimes. I will prove that you are wrong using the power of statistics.
Very well.
But I don't know anything about statistics. I find it scary. I'm going to need some help. Hello.
Hi.
I am Cubit Zenom, king of the zombies. Oh, you look terrible.
Yeah, it's been a pretty intense start to the term.
Is it true that you are the greatest statistician in the land?
Well, I mean, on a good day, I'm barely adequate. But I am available, and I am cheap.
Well, I have been speaking with Azal, head of the werewolves, and he claims that they are scarier than the zombies. I need science to prove him wrong. Can you do it?
Yeah, sure. Leave it with me. Okay, bye.
Thank you.
Well, this is a conundrum, isn't it? I've somehow got to use science to try to work out whether werewolves or zombies are scarier. Well, I can approach this like I can approach any scientific question. So, I have my question to begin with. Are werewolves or zombies scarier? So what I need to do is design some kind of experiment that tests that out. And then I'd need to sample some data, visualize the data, and then fit some kind of model to it to try to ascertain whether werewolves are scarier than zombies or vice versa. And I mean, if I was the, seeing as I'm working for the zombies, I might have a directional hypothesis about that zombies are scarier. But actually, I think I'm going to stay fairly open-minded. Now, we'd fit a general linear model, but this time, unlike in previous lectures, we need our general linear model to reflect differences in fear between two groups, werewolves and zombies. And we need to set up some kind of experiment that allows us to compare the two. But everything else is exactly the same as all the previous lectures. So what we're going to do today is focus on what the general linear model looks like when we're applying it in experimental situations. So when we want to compare groups and see if those groups differ. To recap previous lectures, we've seen that a general linear model is a versatile framework for predicting an outcome from one or more predictor variables. We've used the example lots and lots of times of predicting how long people's ears ring for based on the volume of the concert that they attended. Now in this situation, we can conceptualize the two variables, the outcome and the predictor, as continuous variables. So ringing in ears for a number of hours is a continuum, and the volume of a concert is a continuum. You just have sort of increasing decibel levels. However, we also saw in previous lectures that we could conceptualize the predictor as a categorical variable. So we thought about what might happen if we just took two groups of people. So people who attended concerts and people who did not attend concerts. So we've got two groups here, and we measure their ear ringing in each group. And we mentioned in passing in previous lectures that when we do this, the beta 0 in the model ends up being the mean of some kind of the control group or reference group, and that the beta 1, so the beta attached to the predictor, ends up being the difference between those two means. Now this lecture is going to expand upon that. So I've said many times before, we're going to come back to this in a future lecture. This is the lecture. We've come back to it at last. So if this slide has bemused you in all the previous lectures, then be bemused no more, because all will be revealed. I'm trying to make it sound a fair bit more exciting than it actually is. Okay, so one situation where you might want to compare groups is in experimental research. Now, in experimental research, predictors in the linear model are defined by some kind of experimental manipulation. So you can have naturally occurring groups. For example, people who attend concerts and people who don't are probably quite naturally occurring. Other examples might be what degree subject you're studying. So whether you've chosen psychology or something like medicine or law, they're kind of naturally occurring groups. We wouldn't kind of randomize people to degree programs because we want people to do the degrees that interest them. So you get naturally occurring groups, but in experimental research, you can also get groups where you're trying to actually kind of create a difference by doing some kind of systematic manipulation. So in experimental research, you're using your powers of manipulation to try to see what effect a predictor has on an outcome. So you might randomize people to two different groups, but in one of the groups, something different happens to in the other group. By manipulating a predictor variable rather than just measuring one that naturally occurs, we can make claims about causality, which we can't do when we're just measuring naturally occurring groups. So the power of kind of experimental designs are that they allow us to make causal inferences, to say, this predictor causes the change in the outcome. Ordinarily, we can't do that. We can only do that when we have randomized people to different conditions and systematically manipulated what happens in those conditions. We've covered in previous lectures that the F statistic is used to measure the fit of a model, and that still applies. In fact, everything that we've talked about the linear model in previous lectures still applies, even when we're kind of creating groups and systematically manipulating groups in our research. So the F statistic still quantifies the fit of the model to the data. It still has an associated significance test, but the fit in this case represents an experimental manipulation. It represents the things that you've done to the predictor, so the groups that you've created and the different things that you've done to the groups. So a significant fit, a significant F statistic, when you've done experimental research, equates to a significant effect of the experimental manipulation. And you can then obviously still go on and look at your betas, your parameters. You can still look at them to see kind of what the size of the experimental effect was. But typically the F statistic is used to ascertain whether the experimental manipulation had some effect. So let's have a look at an example. Now, I thought about how to test this hypothesis that zombies might be scarier than werewolves, and I thought we need an experiment. We want to imply some kind of causality. So yeah, we need some kind of situation where people are randomized into conditions, and in one of the conditions they're scared by werewolves, and in one of the other conditions they're scared by zombies. And I thought a good way to do this would be using a kind of a prank design. So I got some inspiration from this clip, which I don't think contains anything too concerning. I don't think it's going to freak you out or anything, but it does contain, someone doing a prank that has a bit of a surprise in it. But it's not that surprising, but it's a bit. Anyway, let's just get on with it, shall we?
Are you from the area, sir?
Is this a movie?
No. I wish it was a movie. You from the area?
I got the evidence back here. Yeah, I put
No. Okay, you're not from the area?
Oh shit! Oh shit! Yo! Oh shit! Oh shit! Oh my god! Woo! What just happened, man?
Now for me, the scariest thing about that clip is the fact that they did that prank near a road that seemed to have cars going on it, because I kind of think if you're going to scare the life out of people and have them potentially run off in random directions, you maybe don't want to do it somewhere where there are passing vehicles. But anyway, I digress. So I thought, well, let's use this experimental design. So we'll have this kind of crime scene design with, a body under a sheet, very Halloween-y. And then, as people come along the road, we just randomize them into one of two conditions. So half of the participants there would be basically a werewolf under the sheet that would jump up and go, "Aah!" And for the other randomly assigned half of participants, there would be a zombie who would jump out from under the sheet and go, "Ah, brains," or something like that. And then we take some kind of objective measure of fear, which, being psychologists, would probably be a fear rating scale from 0 to 10 that has no validity whatsoever. But anyway, that's what we're going to do. Now, imagine that we just randomly took two groups of people and did this prank on them, and we didn't manipulate whether there was a werewolf or a zombie underneath. So maybe there was like just werewolves or something. If we took random samples from a population, we would expect the fear levels to be approximately the same. So we might get something like this. The fear levels in the two groups, they wouldn't necessarily be exactly the same, because we know from previous lectures that you get sampling variability. So if you take two random samples from a population and estimate, in this case, the mean in those samples, the samples will vary slightly. They can be the same, but there's likely to be some small variation in the means that they give you. So you might end up with a scenario like this. The means are roughly the same. So that's what would happen if we just took two random samples and looked at the mean fear scores in those two samples. So that's kind of what we're expecting under the null, under the assumption of no effect, basically. So what happens when we manipulate one of those groups? So when we change something about one of the groups, for example, by putting zombies under the sheet instead of werewolves. Well, what we're hoping here is by doing that, we create some kind of difference between the groups. So we might have a scenario like this, whereby manipulating one of the groups, changing what happens to one of the random samples, we induce a difference in fear levels. So in this case, the second ghoul, now the fear levels are a fair bit higher on average than the first group. Now, what we're trying to ascertain here is, if we take two samples and we measure their fear levels, is this difference in their means plausible just through sampling variation, or is it implausible? Because if it's implausible just through sampling variation, then it's likely that what has created that difference is our manipulation, the fact that some people have experienced zombies jumping up from under the sheet and others have experienced werewolves. So that's the rationale. Now, how do we actually fit a model around this? Well, here's some data. Don't worry about this data. I'm just kind of showing you what it might look like. So we've got some participants with ID numbers. We've got a variable called costume, which tells us basically whether it was a zombie or a werewolf. So if I go down the data, I'm gonna have to go down quite a bit. If we go down the data, we see eventually we get some participants where someone in a werewolf costume jumped out at them. The other thing to note is we've got a fear score for every person. Every person we measured an outcome, their fear. We also have assigned a numeric code to tell us which costume people experienced. Now this is because we can't, the variable costume has words in at the moment, zombie or werewolf, and we can't put words into a mathematical model. We have to put numbers in. So what we do is we convert the words to numbers. So we say, for example, anyone who experienced the zombie jumping up from under the sheet, we are going to give them a 0. So the numeric code associated with zombie is 0. And if we have a look at some of the werewolf people, you'll notice that the numeric code has changed. So if they had a werewolf, we'll jump up at them, we'll give them a numeric code of 1. So these numeric codes are what actually get entered into the model. And where we use 0s and 1s, this is known as dummy coding or indicator coding. And that's predominantly what we're going to be talking about today. There are other ways to code groups. We'll talk about one of those in the next lecture. Okay. So the model we're basically fitting is this. We've got two groups, a group where zombies jumped out from under the sheep. Well, that would be a different kind of experiment and probably slightly more freaky. So a zombie jumps out from under the sheet, and we've got a condition where a werewolf jumps out from under the sheet. Here are the data. So you can see the zombie data on the left and the werewolf data on the right of the plot. And the model we're fitting, the linear model, is represented by that diagonal line. If we write out the equation for the model, our outcome, which is usually denoted by y, we can replace that y with the word fear, because that's what we're predicting. And we're predicting it from an intercept, so beta 0. And we're also predicting it from a single predictor, which generically we always use the letter x, but you can see in the equation below we can replace that x with the variable name, the costume, or actually remember we've recoded that into numbers, so costume would be a series of 0s and 1s. And there's going to be error in prediction, so we've got that e there to remind us of that fact. So if we look at the means of the two groups, it turns out in the zombie condition the mean levels of fear are 7, and in the werewolf condition the mean levels of reported fear are 4.5. So the difference between those two means is what is going to be the beta associated with the predictor. So beta 1, so the parameter associated with costume, is going to be the difference between those two means. So the difference between 7 and 4.5. Beta 0 is going to represent the mean of the group that we have coded with the number 0, which is sometimes called like the reference group. In this case, we coded zombies with 0s, so the beta 0 is going to represent the levels of fear when the predictor is 0, and we know that when the predictor is 0, it's the zombie group. So the beta 0 is going to represent fear levels, the mean fear levels in the zombie group. Our predicted values from the model are the two group means. So if you're in the zombie group, the predicted value of your fear levels from the model will be 7 for everyone in that group, and the predicted levels of fear if you were in the werewolf condition will be 4.5 for everyone in that group. So they're our predicted values. So dummy coding or indicator coding, let's have a look at what happens when we use this. Like I said, there are other ways to code your predictor variables when they're categories, but we're just going to stick with dummy coding today. So with dummy coding, we've coded one of the groups with 0 and one of the groups with 1. And specifically, we decided, and this was an arbitrary choice in this case, but typically you would choose your control group if you have one to be coded with 0, just because it kind of makes the interpretation a bit more straightforward, and your experimental group with a 1. But you don't have to do it that way around. In this case, we decided to code zombies as 0 and werewolf as 1. So we can ask the question, what happens to the model when costume equals zombie? So what does the model look like for, I guess, kind of the zombie group, or when the predictor has a value of zombie? Well, when the costume is zombie, we know that the predictor variable is 0, because that's how we coded it. And we also know that the predicted level of fear from the model is the mean of the zombie group. So we have our model here. We're predicting fear. I'm forgetting about the error term for now. We're predicting levels of fear from beta 0, whatever that may be, and the variable costume, and the variable costume has a parameter, a b, attached to it. So we know in the zombie condition, the predicted levels of fear are the mean in the zombie group. So we can replace fear with mean in the zombie group. That's going to be our outcome. We also know that in the zombie group, costume equals 0. So we can replace the value of costume with 0, and therefore that cancels the beta 1 out. So that tells us that, it cancels beta 1 out. So that tells us that beta 0 is going to be equal to the mean of the zombie group, which is what I told you on the previous slide. Now what about beta 1? Well, let's have a look at what happens when the costume equals werewolf. So when the costume, when the value of the predictor variable is werewolf, we know that the predictor value is 1. That's just how we coded it. So the value of costume in the equation is 1, and we know that the predicted value from the model is going to be the mean of the werewolf group. So we can do a similar thing to what we did before. So we know the outcome, the predicted levels of fear, is going to be the mean in the werewolf group. The value of costume in the werewolf group is going to be equal to 1. So that means beta 1 gets multiplied by 1, so it's just itself. So that leaves us with the mean of the werewolf group being equal to beta 0 plus beta 1. So that's what it represents. But we just discovered that beta 0 represents the mean of the zombie group. So let's slot that in. So beta 0 is the mean of the zombie group. And then if we rearrange that equation to make beta 1 the subject, what that means is we just take the mean of the zombie group over to the other side, and as it passes over the equal sign, it grabs a minus. That just tells us that beta 1, so the parameter estimate attached to the predictor variable costume, is going to be the difference between the two group means. It'll be the difference between the werewolf and the zombie condition. So, to sum this up, we can fit a linear model with fear as an outcome and the type of costume, zombie or werewolf, as the predictor. When we do this, the intercept, the beta 0, will be the mean of the 0 coded group. So in this case, the zombie group, and the b for the dummy variable, the predictor variable costume, is going to be the difference between the means of the two costume groups. So this will be the difference between the mean of 7 and 4.5, which is plus or minus 2.5, depending on which way around you do the subtraction. So I've got it here as minus 2.5 because we coded the zombie group as a 0. So we end up doing the werewolf group minus the zombie group. So 4.5 minus 7 gives us minus 2.5. If we fit the model, we'd get an output something like this, which illustrates all these points that I just said. So beta 0, the mean of the 0 coded group, so it's the mean of the zombie group. We saw earlier on, the mean of the zombie group was 7. And the beta for the dummy variable, for the costume dummy variable, it's going to be the difference between the two means. So the difference between the mean of the werewolf group and the zombie group, minus 2.5, and that is indeed what we get. And you can, this is a parameter like every other parameter, a parameter estimate, just like every other parameter estimate we've looked at in previous lectures. So you can construct a confidence interval around it. You can get a t-statistic for it, and you can get a p-value attached to that t-statistic. So this tells us that difference of 2.5 on our fear scale. Well, first of all, we can interpret that raw effect. So we can say when a zombie costume was used rather than a werewolf costume, then fear was 2.5 higher on that fear scale. We can also interpret its significance. It has a p-value less than the standard critical value of 0.05, so we can say that difference is significant. And we can also look at the confidence interval to try, assume if we make the assumption that this sample is one of the 95% where the confidence interval contains the kind of true difference between group means, then we can say that that difference could be anywhere between about minus 3 and about minus 1.6. I mean, you'd probably want to round off to full digits because it's a 10-point scale. But anyway.
So, Azal, you see, with a smidge of help, I have shown you that zombies are scarier than werewolves. Will you accept this?
I cannot.
Why?
You are not a fool, but you have done a foolish thing.
But I was told he was a statistics genius. Will you let me try again?
Very well.
Hello, it is I, Cubit Zenom, king of the zombies.
Hi.
I took your results to Azal, and he said, you have done a foolish thing.
Really?
I need you to take another look.
Okay, leave it with me.
Bye.
Oh. I've done a foolish thing. That's so unlike me. What have I done that's foolish? Oh! I didn't have a proper control group. I just used zombies and werewolves. I mean, they're both like scary Halloween things. I should have had a control group that was like a non-scary thing. Oh man. That was an error. Okay. Let's redo the experiment, but now add an extra condition, an extra group that has a kind of a proper control of something non-scary or relatively non-scary. So let's have our control as just a general human. So not, werewolves are human wolf hybrids. Zombies are, were once humans. So a kind of an actual, just normal human is probably a good baseline of fear that we should look at, and then see whether zombies and werewolves differ from that kind of baseline. So we can use exactly the same design as before, except now we've got 3 groups instead of 2. So we've got a group where a human jumps out from under the sheet, and then we've got 2 other groups, the same as before, where a zombie jumps out or a werewolf, and our outcome is going to be fear again. So everything's the same as before, we've just now got an extra group. So how does this affect our model? Well, data set's really small. I didn't have much time. I just had to kind of like rush out, set up a crime scene really quickly, randomize a few people, get some zombies and werewolves to jump and humans to jump up at them. And so I've got a small data set. I only had 5 participants in each condition. And these are the mean levels of fear. So when a human popped out, the mean levels of fear were 2.4. They were pretty low on the scale. For a zombie, it was 7.2. It's quite similar to the last study. And a werewolf, 3.8. A bit lower than the previous study. Overall, mean levels of fear were at 4.47, so about the middle of the scale, which I guess is kind of what you would expect. So, our model now has got a bit more complicated because we've got 3 groups. So, this graph represents the fear, each dot is an individual participant. So we've got the 5 dots who had for participants where a human jumped out, then in the middle 5 dots for the participants where the zombie jumped up, and finally on the right we've got the 5 dots for people who saw a werewolf jump out from under the sheet. Now the predicted values from the model are the means of the groups. So in the human, if you were in the human condition, the predicted value of your fear levels is 2.4, the mean of that group. If you were in the zombie condition, the predicted value from the model of your fear levels is 7.2, and if you're in the werewolf condition, your predicted value from the model is 3.8. So this is effectively the model. These predicted, the predicted values from the model are the group means. So how do we do dummy coding when we've got multiple categories? Well, you can code any number of categories into a series of dummy variables. So in the previous example, we just had 1 dummy variable, but you can use multiple dummy variables to code multiple categories. And what you do is essentially enter these dummy variables into the model in a single step. So they all get entered into the model simultaneously. And how you would construct this is to choose a baseline category, which you always code as 0. So this would ordinarily be some kind of control group. In our case, the obvious one being the human group. If you do this, if you just kind of put the variable into the model in R will by default choose the first level of the factor. That's just what it decides to do. So there may be situations where that's fine. There may be situations where you want to override that, and that will be covered in the interactive tutorial. The beta for each dummy variable, so the parameter estimate for each dummy variable, will be the difference in means between each category and the baseline category. So let's have a look at this in practice. This is what we would do. So if you were a person randomized to the group where a human jumped out from under the sheet, then you would be given a code of 0 on the first dummy variable and a code of 0 on the second dummy variable. So the number of dummy variables you have is always one fewer than the number of groups you started with. So we've got 3 groups here. We have to code that into 2 dummy variables. So then what we do is we look at people in, say, the zombie group, and for those people we assign them a code of 1 for one of the dummy variables and 0 for any other dummy variables. So they get a 1 on the first dummy variable and a 0 on the second one. And then anyone in the werewolf condition, it's kind of the opposite. So we give them a 1 in one of the other dummy variables that hasn't already been used, and a 0 for any other dummy variables. So hopefully what is obvious here is that these codes completely describe the 3 groups. So if someone's in the human condition, they get a 0 on both variables. If someone's in the zombie condition, they'll get a 1 on the first variable and a 0 on the second. And if someone's on the in the werewolf condition, they get a 0 on the first variable and a 1 on the second variable. And this, we can actually kind of attach names to the dummy variables based on how we've coded them. So the first dummy variable, everyone is coded with a 0 apart from people in the zombie condition. And what this means is that this is going to end up representing, or the beta for this predictor variable will end up representing the difference between the mean of the zombie group and the human group. And on the second dummy variable, everyone gets coded with a 0 apart from people in the werewolf group. So this group will end up representing the mean in the werewolf group compared to the mean in the human group. Let's have a look at the model. So the model ends up looking like this. So we're still predicting fear levels, and we're predicting it from a beta 0. And we're also predicting it from these 2 dummy variables. The first one we could say is zombie versus human, because that's kind of what it represents. And the second we could say is werewolf versus human, because that's what it represents. So the betas attached to these dummy variables, for example, this beta will represent the difference in means between the zombie and human group. And this beta will represent the difference in means between the werewolf and the human group. So let's delve into this a bit more. So let's again have a look at what beta 0 is going to represent. So let's have a look at the model when the entity is human. So when someone has been assigned to the human group. So we've got our dummy codes on this screen to remind us of what they are. So we know that when the entity is human, the person will get a code of 0 on both dummy variables. So they get a 0 for the first dummy variable and the second dummy variable. The predicted fear levels will be the mean in the human group. So how this plays out is like this. As ever, we're predicting levels of fear from beta 0 and 2 predictors, which are our dummy variables. Now, when someone's in the human condition, this dummy variable is equal to 0, which cancels out beta 1. And this dummy variable is also equal to 0, which cancels out beta 2. So we just end up, the predicted value is the mean in the human condition. So we just end up with the observation that beta 0 is going to represent the mean of the human group. So it represents the mean of whichever category you've used as your reference. So whichever category has got 0 on all of the dummy variables. Let's have a look at what happens in the zombie group. So how do things play out in the zombie group? So when someone's in the zombie condition, we can see that on the first dummy variable they're coded with a 1, and the second dummy variable they're coded with a 0. The predicted fear from the model is going to be the mean of the zombie group, because that's the group we're looking at. So looking at the model, it plays out like this. So So we've got the same model that we've looked at before, but now the first dummy variable, that will be a value of 1. The werewolf versus human is a value of 0. So that 0 cancels out the beta 2, and beta 1 gets multiplied by 1, so it remains as itself. And the predicted outcome is going to be the mean in the zombie group, because that's the group we're now looking at. So we can see that the mean in the zombie group equals beta 0 plus beta 1. But we know from the previous slide that beta 0 represents the mean of the human group. So this is the mean in the human group, so we can swap that in, which leaves us with the observation that beta 1, the beta attached to the first dummy variable, is the difference between the mean of the zombie group and the mean of the human group, which is what I said it would be. And finally, we can do all of this again, looking at the werewolf group. So in the werewolf group, anyone in that group is coded with a 0 on the first dummy variable and a 1 on the second dummy variable. The predicted fear from the model is the mean in the werewolf group. So we can work through that in exactly the same way as we did before. So now if someone's in the werewolf group, the predicted levels of fear are the mean in the werewolf group, so we can substitute that in. On the first dummy variable, zombie versus human, that's going to be a 0, so that cancels the beta 1 out. And the werewolf versus human dummy variable is going to be 1, which means that beta 2 gets multiplied just by 1, so it stays as it is. So this tells us that the mean of the werewolf group is going to be equal to beta 0 plus beta 2. If we rearrange that equation, that tells us that beta 2 is going to be equal to the mean in the werewolf group minus beta 0. And as we know from a couple of slides ago, beta 0 is equal to the mean in the human group. So beta 2, the beta attached to the second dummy variable, ends up being the difference between the werewolf group and the human group, as I said it would be. Well, that's nice, isn't it? So if we go back to our model, here are the predicted values. Beta 1, the parameter beta 1 is going to represent the difference between those two means. The parameter beta 2 is going to represent the difference between the werewolf and the human mean, so it's going to represent the distance displayed on the graph. So what will those parameter values be? Just to remind you of what the means are. 2.4 in the human group, 7.2 in the zombie group, and 3.8 in the werewolf group. So beta 0 is going to be the mean in the human group. It should be 2.4. Beta 1 is the difference in means between the zombie and human group, so that's going to be 7.2 minus 2.4, which is 4.8. Just make a mental note of these final values, and the beta 2 is going to represent the difference between the werewolf and the human group, so that difference will be 3.8 minus 2.4, or a difference of about 1.4. Like I said, the model looks like this. We're predicting fear from our 2 dummy variables, and they'll have parameter estimates attached to them. So we could replace these values of the betas with the values that we just worked out. Beta 0 we just worked out was 2.4, beta 1 we just worked out was 4.8, beta 2 we just worked out was 1.4. So we could slot those in. So if we wanted to predict fear based on what entity sprang out at someone, we could do that by just simply replacing zombie versus human with either a 0 or 1, and werewolf versus human with either a 0 or 1, depending on which group people were assigned to. Okay, now we've got lots of parameters here. So first of all, we would look at the overall fit of the model. So how well can we predict, or how much better can we predict fear levels as a result of using the group means as our predicted values? And these slides are just, you don't need to process them too deeply. It's just to illustrate that what goes on behind the scenes is exactly the same as when we looked at the F statistic before. There's nothing different. The only thing that's really different is what the predicted values from the model are. So we saw before the total sum of squared errors is the difference between each observed value and the overall mean level of the outcome variable. So this is the difference between each person's level of fear and the mean level of fear. We saw that we square those differences and then we add them up to get a total amount of error. So the total sum of squared error is calculated exactly the same as when we did it before. The residual sum of squared errors is the difference between the predicted values from the model, so the values predicted by the line, and the observed values of the outcome for each person. So here, although we don't have a diagonal line like we've looked at before, we've got sort of 3 flat lines, the principle is exactly the same. So we're just looking at the difference between what's predicted and what was actually observed. What was predicted for each person is the mean of their group, and we're just looking at the difference between that mean and each observed value. Again, we square these errors because some of them are positive, some of them are negative, and then we would add them up really to get some kind of total. So the sum of squared errors, again, it's calculated in exactly the same way. And the model sum of squared errors, well, now when we looked at this before, we saw that this was the difference between the error in the model when the model is fitted versus when it's not fitted. So we're looking here at the difference between the predicted values and the overall mean of the outcome. So in this case, for each participant, we no longer look at their observed score, we just look at their predicted score versus the kind of overall mean levels of fear. So for each person, we're looking at the difference between the mean of their group and the mean of all scores, regardless of group. Again, these errors get squared, they get added up. Process is exactly the same as for any other kind of predictor variable. And as we've seen before, we can then use these sums of squares, we can convert them to mean squares, and having done that, we can compute an F statistic, which is the ratio of how well the model fits to how much error there is. Now, in the case of this kind of experimental manipulation where you've got several groups of people, the model is difference between means, so the F statistic is going to be the sort of ratio of experimental effect to the background noise or background error. So basically the F statistic is going to test whether group means differ overall, but it's not going to tell us specifically which means differ. So it will tell us whether wearing a different kind of costume affects fear levels. It won't tell us which costume in particular affects fear levels. And to find out which costumes affect fear levels, we would then look at the parameter estimates. We would look at the B's and their significance tests to break down this overall fit. So looking at the overall fit when we actually fit this model to these particular data, we get an F statistic of 5.02 with a p-value of 0.03, and the R square is pretty substantial at 0.46. So about 46% of the variance in fear scores is kind of accounted for by group membership. So we could report this as the type of monster in the prank had a significant effect on fear levels, and we'd report F with 2 and 12 degrees of freedom is equal to 5.02. Could report the p-value as it's actually 0.026 if you look at a few more decimal places, but 0.03. And we might also report the R square as being 0.46. So basically it looks like the costume that was worn does have a significant effect. To find out which costumes in particular have an effect, we could look at the parameter estimates. So these are the parameter estimates for the model, and we can see from this, first of all, if we look at the dummy variable that represented zombies versus humans, its parameter estimate is 4.8, which is what we said it would be. That's the value we calculated earlier on. The p-value attached to that, which is computed via the t statistic, is in fact significant. So that suggests that zombies or fear levels were significantly higher when a zombie costume was worn compared to a human. And we've got a confidence interval for that beta as well. When we look at the dummy variable for werewolf, so this is comparing werewolf against humans, we get a parameter estimate of 1.4, which again we calculated earlier. That is the difference between the two means. That has a t statistic as well and an associated p-value, which is not significant. So it kind of suggests that zombies are significantly scarier than humans, but werewolves are not significantly scarier than humans. Now, this is a linear model, and just like any linear model, we would test assumptions. So we would have a look at residual plots to see kind of what our assumptions look like. The top two plots are telling us about heteroscedasticity, and the bottom left plot is telling us about normality of residuals, and the bottom right plot tells us about Cook's distance. Now, all of the Cook's distances are well below 1. The maximum value is 0.3. There's nothing, it doesn't look particularly like anything's influential there, so we probably don't need to worry about that. In terms of heteroscedasticity, there might be potentially an issue, because if we look on this plot, the sort of trend line is not very flat. It's got a bit of a spike to it, which kind of suggests there might be heteroscedasticity in the residuals. And looking at normality, this is the least problematic of the lot, but looking at normality, we're getting a sort of snaking around the line. It's not too dramatic. It's probably not anything much to worry about. So of everything, heteroscedasticity might be something to concern ourselves with in this model. So one way to combat heteroscedasticity is you can, if you're just worried about the overall F test, F statistic, then you can fit something called the Welch F test fairly straightforwardly, and this is robust to heteroscedasticity. So this is what I've done here, just to verify, it's kind of a sensitivity check really, that when we fit a robust version of F, we still get a significant result. So this gives us confidence that, type of monster in the prank had a significant effect on fear levels, even when we use a robust measure. And we would report that with 2 and 7.74 degrees of freedom. The value of F itself is 6.89, and the P is 0.019. We could also look at the parameter estimates when we use a robust standard error. We've talked about these in previous lectures. So these are just the parameter estimates, which the estimates themselves don't change, but we could look at the significance tests and confidence intervals when we use a robust standard error. This would also kind of combat the effects of a potential heteroscedasticity. And basically our zombie dummy variable is still significant, and we would look at this revised confidence interval. Our werewolf dummy variable is still not significant. Again, we could look at the revised confidence interval as well. Basically, again, this is a useful sensitivity check that even when we use sort of robust methods, our basic conclusions don't change. So it still seems like werewolves are scarier. Zombies are scarier than humans, but werewolves are not.
Azal, I have returned, and this time we have not done a foolish thing, but instead we have shown that zombies are indeed scarier than humans, but werewolves, cuddly little werewolves, are not. Ha ha!
I was working in the lab late one night when my eyes beheld an eerie sight, for the means of my groups didn't look the same. I couldn't fathom why with my peanut brain I did the F. I did statistic F, I did the F. Because I felt bereft, I did the F. I had nothing left, I did the F. I did statistic F. The variance explained was more than not. But was it a little? Was it a lot? My sums of squares were incomparable, so I compared the mean squared model to residual. I did the F. I did statistic F. I did the F. Because I felt bereft, I did the F. I had nothing left, I did the F. I did statistic F. so I did a dance, because under the knoll that F was unlikely by chance. But I still didn't know which means differed, so looked at tests of my model parameters. I did the F, I did statistic F, I did the F, because I felt bereft. I did the F, I had nothing left. I did the F, I did statistic F.